Hello, AP Calc BC. This is Chapter 10, Topic 5. So the last topic in our curriculum. This is about the area enclosed by polar curves and a polar gallery. So in years past, the AP exam has expected you to be able to recognize all of the basic polar curves, just like you might be able to recognize a linear function, a quadratic function, a square function, an exponential, logarithmic, and so on and so forth. You should be able to recognize all of the polar functions. Now, this year, with the exam being shorter and online, I don't know what they might have on there related to polar functions, but we still want to carry out the course in the same way that we would in the past and cover as much material as we can and to the best of our ability as we can. What they might do is take a lot of problems and combine a lot of topics in one, so that might be how you see polars worked in. The area enclosed by polar curves, just about every single year I've done the AP exam, I've seen a few multiple choice questions on this, or one whole free response question on this. So this is kind of a big topic. It's kind of what makes BC Calculus. Now, I don't know with the exam being a shorter amount of time this year, if they'll do that, but definitely something that you should be familiar with. Okay, so our objectives, by the end of this, you should be able to use integrals to calculate the area of the region enclosed by polar curves and identify some common polar graphs using forms of their functions. Okay. So what is the area enclosed by a polar curve? Well, when we started using integrals to find area months ago, we would have some kind of curve, and we started off by finding the area by dividing the area underneath the curve up into rectangles, and each rectangle would have a uniform width of delta x, right? And then we would just find the height, which would be the point of the function there, your y coordinate there along the curve, and then you would approximate all of those areas and add them up. So we can do something similar with polar curves. Because polar curves, you kind of think about them as having a radius and an angle and being some rotation around another point. Instead of dividing them up into rectangles, we're going to divide them up into sectors, much the same way we would divide a circle up into sectors. So we're going to be creating these very thin sectors of area. And when we were doing area using rectangles, we were making the rectangles as thin as we could and letting delta x approach 0. And here we're going to want to let delta theta approach 0. Okay? So the area in a polar shape is going to be the sum of sectors of circles, right? So you can kind of think about this as dividing it up into an infinite amount of very thin sectors going the whole way around and then adding them all up. So if you remember from geometry, the area of a sector is 1/2 r squared theta, where r is going to be the radius and theta is the central angle, and for calculus we typically almost always use radians. If we replace theta by the differential d theta, we can get the area differential, which is dA is 1/2 r squared d theta. And that's exactly the quantity that we need to integrate to get our area and polar coordinates. Okay? So we would have 1/2 r squared d theta, and d theta is just this very small increment of theta. Okay? So we've got kind of this formula. The area and polar coordinates. So let's say you're trying to find the area between the origin and the curve, which is some function of theta, between two angles alpha and beta. It's going to be the integral from alpha to beta of 1/2 r squared d theta. And r, remember, is the same thing as the function of theta. So the other way that you could think about this is the integral from alpha to beta of 1/2 of the function of theta squared, d theta. So for example 1, we want to find the area of the region in the plane that's enclosed by this cardioid right here. And the function for this, r, is 2 times 1 plus cosine theta. Okay, so the area inside this heart-like shape. so. Alright, now, so the example that we had gave us a graph of this, and on the AP exam, whenever I've seen questions like this come up, they almost always give you the graph, and they even highlight a few points on it, give you a few intersection points. They try to make it easy for you, well, not super easy, but they try to make it so that the question is really only focusing on your knowledge of the integral and not silly little graphical things, okay? So I wouldn't be surprised if on the AP exam they gave you this with a whole lot of hints. See, look, they've got 4 here, they've got 2 here, right? Okay, they remind you theta's going from 0 to 2 pi, so they definitely could do something like that, and they could even give you a few intersection points if more than one function was involved. What they really want to test is your knowledge of how you apply all of this going through the overall process. So by graphing it, you can see that this radius OP will sweep out the region exactly once as you go from 0 to 2 pi, right? So if we start at 0 and we kind of wrap around, we're going to go through the whole region once, okay? So then what we could say is, well, we're going to use the formula that we were given just a few minutes ago. Area is going to be the integral from alpha to beta of 1/2 r squared d theta. And remember, r squared could be our function of theta squared. So our initial and final angle here will go from 0 to 2 pi of 1/2, and then my r is going to be 2 times 1/2, or I'm sorry, 1 plus cosine theta, and that's squared d theta. Okay, so now we can go ahead and simplify some things. So we've got the integral from 0 to 2 pi, and I've got this, let's see, this 1/2, and then, well, this 2 is going to get squared, so we'll square that, that's 4, and then this stuff on the inside gets squared, so that turns into 1 plus 2 cosine theta plus cosine squared theta d theta. And 1/2 of 4 is 2, so then what I'll do, let's see, I'll go from 0 to 2 pi, and I'll have 2 times 1 plus 2 cosine theta plus cosine squared theta d theta. And then if I distribute this 2 the whole way through, that'll give me 2 plus 4 cosine theta plus 2 cosine squared theta d theta. Now, it would be nice to make this easy to integrate for us, and we could use a double angle identity here. Alright, so if you recall that really quickly, so I'm going to use my double angle trig identity, which says that cosine 2 theta is the same thing as 2 cosine squared theta minus 1. So then if you work through this and you try to get cosine squared theta by itself, you'll get cosine squared theta is cosine 2 theta plus 1 over 2. Okay, so then what I can do here is I can take this and sub that in for this piece right here. And if this is divided by 2 and this is multiplied by 2 right here, those 2's are going to cancel. So then my next step, what I'll have is the integral from 0 to 2 pi of 2 plus 4 cosine theta plus, okay, so now this 2 cancels, and I'm subbing this identity, and then this 2 in the denominator cancels to get cosine 2 theta plus 1, right? And then we're all evaluating this, or integrating this with respect to theta. So this is going to be the integral from 0 to 2 pi of 3 plus 4 cosine theta plus cosine 2 theta d theta, right? And the antiderivative of that is just going to be, that'll be 3 theta plus 4 sine theta plus sine 2 theta over 2, evaluated from 0 to 2 pi, right? And so then, if we copy that down, so I have 3 theta plus 4 sine theta plus sine 2 theta over 2, evaluated from 0 to 2 pi. So if we plug 2 pi in, this is going to give us 6 pi, sine of 2 pi is 0, sine of 4 pi is 0, and then if we plug 0 in, that's going to be 0, 0, 0, so your answer is just 6 pi. Okay, so the area of this cardioid that we were looking at is 6 pi. Now, if you notice, the double angle identities came up, and they come up quite a bit with polars. So, and we've seen them come up in other areas in calculus. So I would definitely make sure that you know these before the exam. Okay. So that was example 1. If we go on to example 2, okay. We've got this next piece right here. So we want to find the area inside the smaller loop of the limacon. So the limacon is this shape that has this tiny little loop or keyhole on the inside. And we want to find the area just inside that. Okay? Now, so this point right here, you can think about this point as 0, theta, right? And if you notice, this theta, if you track the whole thing, we go around and then we come on the inside and we form that angle. The theta is where it intersects itself, and so that's going to be the angle. Where you cross 0 is going to be where you start and end your keyhole right here. Okay, so what we have to do is we have to find theta, and then once we do that, that'll give us the bounds of our integral, and then it's pretty easy from there. So we know that it's going to hit that angle whenever our radius is 0. So we could start off with 0 is 2 cosine theta plus 1. So subtract 1, negative 1 is 2 cosine theta, and then cosine theta is negative 1/2, okay? Well, cosine theta will be negative 1/2 at reference angles of pi over 3. And you know that cosine is going to be negative in quadrants, let's see, we know cosine will be negative in quadrants 2 and 4. Yeah. Okay, so in quadrants 2 and 4, and so if we have a reference angle of pi over 3, so we're going to say that theta is going to be pi minus pi over 3, which is 2 pi over 3, and theta is going to be pi plus pi over 3, which is 4 pi over 3. Okay, so what happens is when we're at 2 pi over 3 and 4 pi over 3 radians, that's when we're at a radius of 0, and that in between that interval is when we're forming this smaller loop inside the lemma sun. So our integral, the area of this, is going to go from 2 pi over 3 to 4 pi over 3. And it'll be 1/2 r squared theta. So 2 cosine theta plus 1, the whole thing squared, d theta. Okay? And I'll take this to another piece of paper. So our area is going to be the integral from 4 pi over 3 to 2 pi over 3 of 1/2 2 cosine theta plus 1, the whole thing squared, d theta. So we can go ahead and square all of that. And let's see. So we'll still have 1/2 times 4 cosine squared theta plus 4 cosine theta plus 1 d theta. Now this is something that I would use nint. Okay, because I'm looking at this, and this could be a little bit of a mess trying to find our antiderivative. So if we nint this, our area is going to be 0.544. And so that's the answer, and we're all done. Alright, so area is 0.544. Right. So, let's see, we talked about now the area between polar curves. Okay, so the area between polar curves, that's going to be the area of the region between your two functions, right? And it still matters what our angles are going to be, where we start theta and where we end theta. And so how we do this, it's the same formula, 1/2 r squared d theta from your initial angle to your final angle. But how you can think about this is the outer function minus the inner function. And so the tricky thing sometimes with polars is understanding which one's outer and which one's inner. And sometimes they cross, so then you might have to set up two integrals. Okay? And so you can simplify it, r squared, outer squared minus inner squared, and do it all with one integral like we have set up right here. And so that's what we're going to do with excuse me, example 3. For example 3, we want to find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Okay, so our circle r equals 1 is going to be this blue line. Okay, and then the cardioid, 1 minus cosine theta, will be the green line. Okay? And so you always want to visualize these first and either sketch them or graph them on a calculator. And so if we're thinking about this region here, well, if we look at that, we can see that the outer curve is going to be the circle r sub 2 equals 1. Okay, so this this is your outer. Okay, and the inner curve is going to be r sub 1 is 1 minus cosine theta. So your inner curve is the green guy. Now, this is an example of some really nice information that they give you, and they could very easily do the same thing on the AP exam for this type of problem. They give you, okay, so you can see that they intersect at these points here, and they give you those points. excuse me. So your lower limit is theta is negative pi over 2, and then your upper limit is pi over 2. So we know our integral is going to go from negative pi over 2 to pi over 2, and it's going to be 1/2, and we'll do r sub 2 squared minus r sub 1 squared d theta. Right, so we've got negative pi over 2 to pi over 2, and then, well, our outer r sub 2, if we square that, we're just going to get 1, and then our inner is 1, the quantity 1 minus cosine theta, the whole thing squared, d theta. Okay, so we can kick that over here. So we'll have the integral from negative pi over 2 to pi over 2 of, let's see, 1/2 times 1 minus, okay, and then squaring this, that'll be 1 minus 2 cosine theta plus cosine squared theta d theta. So we're going to have, let's see, from negative pi over 2 to pi over 2, so 1 minus 1 plus 2 cosine theta minus cosine squared theta d theta. Okay, well 1 minus 1 is just going to cancel, and then we can distribute that 1/2. So I'll have, let's see, 1/2 times 2, so that'll be cosine theta minus cosine squared theta over 2, okay, d theta, and here we've got this nice and simple, so this should be pretty easy to plug into our calculator, hopefully without making too many mistakes. And then we can practice our NINT skills. We're going to get 1.215. And that's the answer there. Okay, so that's the area between these two curves. So that was example 3. The last thing in this section is just a gallery of the common polar curves that you should know before the exam. So some of these are really easy to remember, and some of these are a little trickier. They have some patterns with these, so I would definitely go ahead and make some flashcards and start studying a few of these every day before the exam. So when your radius is a constant, that's just going to be a circle, and your interval there is from 0 to 2 pi. R is a sine theta. Your circle will be shifted up on your y-axis. That's easy to remember. How I always remember that one is because typically we associate y with sine. So then likewise, we also associate cosine with x. So r equals a cosine theta. That's going to be on your x-axis. Okay? And notice the interval for this one goes from 0 to pi for both of these. And how I always remember that one is because if you see where the circle is, it only covers about 180 degrees of the coordinate plane, right? So in this case, it's the upper half of the graph, and in this case, it's the right half of the graph. So it only covers about 180 degrees of the graph, so that's why those go to pi. All right, and then you can have flowers with odd numbers of petals. So a sine n theta, when n is odd, you'll have that many petals, n petals, and you'll have y-axis symmetry, and you're only going to be going from 0 to pi. When n is even, you will have 2n petals, and you'll have y-axis and x-axis symmetry. If you flip this around and you have cosine, if you have a cosine n theta and n is odd, then you'll have n petals and you'll have x-axis symmetry. And then if you have a cosine n theta again and n is even, you'll have 2n petals and you'll have y-axis and x-axis symmetry. So one thing to notice with sine and cosine, when n is even, you have 2n petals and you have symmetry on both axes. Okay? If n is odd, well, you only have symmetry on the x-axis if it's cosine, which makes sense because we associate cosine with x, and you only have symmetry on the y-axis when n is odd. If it's sine, and we usually associate sine with the y-axis. So some ways that you can remember those. And then the limit-sum curves are a little bit trickier to memorize. So these functions are going to be r is a plus or minus b sine theta, or r is a plus or minus b cosine theta. So how these are different from the ones that you just saw is you're going to have some constant added or subtracted to the sine or the cosine theta. For all of these, well, except for the dimpled one, you'll be going from 0 to 2 pi. And you can see with sine theta you have y-axis symmetry, with cosine you have x-axis symmetry. When your ratio of a to b is less than 1, you'll have a limison with a loop. When the ratio equals 1, it'll be a cardioid, and it'll be a heart, and you won't have anything on the inside of it. When your ratio is between 1 and 2, it'll be dimpled, and notice there that your interval only goes from 0 to pi. And then if it's convex, that means that one of these sides is a little bit flatter than the other. A over b, your ratio of a over b is going to be greater than or equal to 2. And then we have the Lemniscate curves. So you could have r squared is a squared sine 2 theta, and r squared is a squared cosine 2 theta. So in both cases your interval goes from 0 to pi, and how these are different from what we just saw, you have an r squared term here, and then your initial coefficient is a square. And then also you've got this 2 theta there. Okay, so that makes things different. And then the spiral of Archimedes, well, that is just r equals theta, and we have to say theta is positive. I've never seen this come up on an AP exam, but there you go. Maybe something interesting to know if you take some higher math courses or if you're ever on Jeopardy. Okay, so that's the end of topic 5. That's the end of the calculus curriculum. I'm really sorry that we weren't together to finish it all in person, but we did it, and hopefully I will get to see you all again sometime before the AP exam, but if not, we'll have lots of fun reviewing virtually.